Hello everyone. Today we are tackling a topic that scares a lot of students, virtual memory. But I promise you, by the end of this video, you will think this is the coolest invention in computing history. Let me ask you a question. A modern video game is often 100 gigabytes in size, but your laptop only has 16 gigabytes of physical RAM. Mathematically, 100 cannot fit inside 16. It is physically impossible. Yet, you double-click the icon and the game runs perfectly. How? The answer is a clever illusion managed by the operating system called virtual memory. Before we see the magic, we need to understand why we need it. Without virtual memory, we hit three massive walls. First, the limited size. As we just said, programs are huge. Without virtual memory, if you have 16 gigabytes of RAM, you can't run a 17 gigabytes program. You are limited by the physical chip. Second, no protection. In the old days, all programs lived together in the same physical RAM house. Imagine this. Your web browser is a messy roommate. It has a bug and it accidentally writes data into the memory space of your word processor. Boom! Your essays and notes are gone. The whole system crashes. Without protection, one bad program kills everything. And third, no convenience. This is a nightmare for programmers. If you had to manage physical RAM directly, you would have to know exactly which memory cell address to use. It's a logistical nightmare. So, how do we solve this? We lie. The core idea of virtual memory is to decouple or separate the address the program thinks it has from the address the RAM actually uses. We create two worlds. One is the world of virtual address. This is the fake address. Every program believes it has a huge continuous block of memory starting at 0. It thinks it owns the whole machine. And another is world of physical address. This is the real address on the actual green RAM stick inside your computer. But how do we connect the fake world to the real world? Meet the star of the show, the MMU, Memory Management Unit. This is a piece of hardware on your CPU that acts as a real-time translator. Every single time your program tries to read data, the MMU intercepts it. CPU says, "Give me address 1000." MMU thinks, okay, for this program, address 1000 is actually physical address 99. Then MMU says to RAM, "Give me address 99. The program never knows it was tricked. It lives in the matrix. So, how does this translation trick actually solve those problems we talked about? First, the size solution. Because the addresses are fake, they can be huge. On a 64-bit system, your virtual address space is 16 exabytes. That is nearly infinite. The operating system keeps your massive program on the slow hard drive. We call this the backing store or swap file. It only brings the tiny pieces you need right now into RAM. You get the size of the disk with the speed of RAM. Second, the protection solution. This creates a perfect sandbox. Imagine program A writes to virtual address 1000. The MMU puts it in physical spot 5. Now, program B also tries to write to virtual address 1000. Does it overwrite A? No. The MMU translates program B's 1000 to physical spot 99. They use the exact same virtual numbers, but physically, they are miles apart. They are completely isolated. Now, to truly understand the concept of virtual memory, let's use the library desk analogy. This will make it click forever. Imagine you are a student representing the CPU. Your tiny desk is your physical RAM. The desk can only hold 3 books at a time. The massive library behind you is your hard drive. It holds millions of books. Now, the illusion of virtual memory is like you want to believe you have the entire library sitting right on your desk. You don't want to get up. You want to just reach out and grab any book instantly. And there is your invisible magical librarian, MMU, who will connect your illusion to real world. Now, you ask for the book, Harry Potter and the Goblet of Fire. The MMU checks the desk. It's there. Great. Then you ask for the book, Harry Potter and the Chamber of Secrets. It's there. Great. Now, you ask for the Harry Potter and the Deathly Hallows. It is not on the desk. The desk is full. Does the system crash? No. The MMU pauses you for a microsecond. It runs to the library, grabs Harry Potter and the Deathly Hallows, and swaps it with a book you aren't reading right now. To you, it felt like that book was there the whole time. You are happy the desk didn't explode. And the protection? Imagine another student sits next to you. That's a different program. Virtual memory gives them their own desk. Even if they spill coffee, which is a bug, they spill it on their desk, not yours. You are completely isolated. So, we have the concept, but how does the OS manage this swapping without losing track of millions of books? That can be done using two strategies. So, let's see the first one, paging. Now, how do we actually build this illusion? The most common method used by Windows, macOS, Linux, and Android is called paging. Now, this is the concrete definition for your theoretical question answers. Let's understand paging thoroughly, otherwise you won't understand. Now, here the core idea is that we chop up the entire virtual memory into small fixed size blocks called pages, usually 4 kilobytes. And we also chop up the physical RAM into the exact same sized blocks called frames. The job of operating system is that it simply takes a page from the program and fits it into any available frame in RAM. It's like Lego bricks, they always fit perfectly. But if page 1 is in frame 50 and page 2 is in frame 99, how do we keep track of the mess? We need a map, and that's the page table. The OS stores and keeps track of this mapping between logical addresses and physical addresses in a large data structure called a page table, which is stored in RAM. It answers one question: where is virtual page X located in physical RAM? Now, watch closely. This is the exact magic trick the MMU hardware performs for every single mouse click or keystroke. When your CPU issues a virtual address, the MMU slices it into two specific parts: the offset or the bottom bits. This is the specific byte inside the page. Since our pages are 4 kilobytes or 2 to the power 12 bytes, the bottom 12 bits tell us exactly which byte we want inside that page 1. Here, you should know that the offset never changes. If you want line 10 on the virtual page, you want line 10 on the physical page, the MMU just copies this part directly. And the virtual page number, or VPN, the rest of the top bits are the VPN. This is the ID card. It tells us which specific page of the program we are looking for. So here is the workflow. The MMU takes the VPN and uses it as an index to look inside the page table. The MMU reads the page table entry at that index. This entry contains two key things: the valid bit. It answers the question, is this page in RAM? If valid bit is 0, the page isn't there, and if 1, then it is. And other one is the physical frame number, or PFN, which is the real location in RAM. This effectively says virtual page 5 is currently sitting in physical frame 99. Assuming the valid bit is 1, the MMU takes the PFN from the page table and recombines it with the original page offset. This creates the final physical address, PFN, and 12 bits page offset. And that new address is sent to the RAM. Now, if the technical process is making your head spin, let's look at it this way. Imagine, it is the second day of your 11th standard in school. I know you're in university, but for a second, let's go back to the good old days. Okay, so now you are late. You are panicking. Your brain is thinking in virtual terms. You scream, "Oh, I'm so late, I need to get to chemistry class." And there, I sit in seat 5. Chemistry class is not a physical location. You can't walk into a room labeled chemistry. That's a virtual concept. The school, representing the RAM, is just a maze of numbered rooms. Room 101, room 202, room 404. So, you stop and look at your schedule, which is the page table. You find chemistry. The schedule says, chemistry is in room 404. And this is your PFN. Now, does the schedule tell you which seat to sit in? No. You already decided you want seat 5. Maybe it's near someone special. Who knows? So, changing room label from chemistry to room 404 doesn't change your seat preference? So, your virtual thought was chemistry class plus seat 5. And the physical reality is room 404 plus seat 5. Now, you sprint to room 404 and sit in seat 5. If you had gone to the wrong room, which means wrong translation, you'd be sitting in Seat 5 of a history class looking totally confused that where is she or where is he? Or even why there's Alexander the Great in chemistry. So that is address translation. replacing the subject with the room number, but keeping the seat exactly the same. But what if the page table says, not here? What if the valid bit is 0? This means the data isn't in RAM, it's still back in the library, the hard drive. This triggers a page fault. A page fault is a hardware-raised exception or interrupt that occurs when a program accesses a virtual memory page that is currently not present in physical memory RAM. But don't panic. Page fault isn't an error. It's a trap that pauses the program and gives the whole control to the OS. The operating system handles thereafter. First, the OS saves the user registers and process state till now into the process control block or PCB. Then, the OS checks the internal tables to determine if the reference was an invalid or illegal address. If it is, then OS terminates the process. But if the reference was valid, but the page isn't in RAM, then OS proceeds to page in. What is page in? I'll say just a second later. Before that, the OS searches for a free frame in the physical memory. If no frames are free, a page replacement algorithm like LRU or FIFO is executed to evict a victim page. If you want, you can check out the video on page replacement algorithms in our channel under cache memory. Okay, now, after finding a free frame in RAM, the OS issues a disk I/O request to read the desired page from the backing store into the newly allocated physical frame. This operation of loading the page to frame is called paged in. Now, once the disk read is complete, the page table is updated with the new frame number and the valid bit is set to 1. Now, the OS restores the PCB and it rewinds the program and lets it try again. And the program never even knows it was paused. To the program, it was just a tiny hiccup. We have one final problem: speed. The page table itself lives in RAM. So, to fetch data, we have to first go to RAM to read the page table and to get PFN. Only after the PFN is retrieved can the MMU form the final physical address and access main RAM again to retrieve the actual data the program wanted. So, we just doubled our work. Every single memory access now requires 2 total memory accesses. This cuts performance by 50%. That is unacceptable. So, the solution? The TLB translation, Lookaside Buffer. This is a small, extremely fast, fully associative hardware cache built right into the MMU. It stores the most recent translations. So, how is the real address translation process with the TLB? Look, in the same way as paging, CPU issues a virtual address. MMU splits it into VPN and offset. Now, MMU checks the TLB, just a one-cycle, on-chip check. For TLB hit, which happens almost 99% of time, the VPN is found in the TLB. The PFN is taken immediately from the TLB and the full physical address is built and sent to RAM. Total cost is just 1 memory access. The translation was free. But for a TLB miss, the VPN is not in the TLB, so the CPU stalls. The MMU must now do the slow lookup. Go to the page table in RAM to find the PFN. That VPN to PFN translation is loaded into TLB. Then the translation is rerun, which now results in a TLB hit. Now, here total cost is 2 memory accesses, but this is just 1% of the time. The TLB is the only reason virtual memory is fast enough to use today. So, let's take a breath. Today, we unlocked the massive illusion of virtual memory. We learned how the MMU tricks the CPU into thinking it has infinite space. We learned how paging chops everything into neat little 4 kilobytes Lego bricks. And we learned how the TLB saves us from walking to the library every single time. But ask yourself this: does a real computer program actually look like a pile of 4 kilobytes bricks? No. A program has a code section, a data section, a stack, and they're all different sizes. Paging ignores that structure. Is there a more logical way to organize memory? The answer is segmentation, and that is exactly what we will cover in the next video. Hit that subscribe button so you don't miss it. Thank you.